Hi, my name is Mehryar Rahmatian from University of California at Irvine.
And my name is Hessam Kooti.
The project we are going to present in DAC 2011 University booth is FPGA-based intrusion detection for embedded system security.
This project is done under supervision of Professor Harris and Professor Bozorgzadeh from ICS department of UCI.
We found security of embedded systems rather an open question that needs more attention. But what makes embedded security different from desktop computers? Embedded systems are often highly cost sensitive. Many embedded systems interact with the real world. The internet can be a dangerous place. High network bandwidth of today's network is useful for attackers who can take over our computers. Also, most of embedded systems have performance constraints. Many real-time applications are implemented using embedded systems. Our computers are always under attack. In recent report, 48% of 22 million scanned computers were infected with malwares. On April 2009, the Pentagon announced that they spent more than 100 million in the last 6 months responding to and repairing damage from cyber attacks. This shows the importance of intrusion detection systems. Intrusion detection is the process of observing system behavior to identify inappropriate activities. That's basically what you do after all preventions and firewalls fail to detect attacks, so it captures the attacks which are in progress. Our system is no silver bullet to detect all kinds of intrusions, but we claim that we can detect one of the most common penetration, which is execution of corrupted code. Our approach seeks for any anomaly which involves detecting of execution of shell code by comparing the behavior of the executing code to the known behavior of correct code. Software-based intrusion detection suffer from following drawbacks. First, large performance degradation due to constant monitoring operation inserted in application code. Moreover, they are unable to detect intrusions in near real time, and this time lag could prove disastrous in real-time embedded systems. On the other hand, hardware-based intrusion detection systems are much faster than software counterpart, which is desirable for real-time embedded application. Plus, hardware reconfiguration enables us to adapt the executing process on the system. The architecture of our intrusion detection system is shown here. The syscall detector block receives information from the microprocessor and uses it to detect the execution of system calls. The syscall detector has two outputs, syscall P, which indicates the execution of system call, and syscall num, which is the number of system calls being executed. The syscall sequence recognizer implements a finite state machine which only accepts all the legal sequences that can be generated by correct program. If the syscall sequence deviates from the non-correct sequence, then the state machine enters its detection state and asserts attack detected output. Our benchmarks are well-known C programs such as BubbleSort, Telnet, INetD, and FTP. We measure area and performance overheads imposed by our technique to the existing system. As an example, in case of FTP, we have only 0.7% area overhead and 0.2% performance overhead.
Now we will perform our technique on a Lion processor implemented on the Xilinx Vertex 5 board. As we said earlier, we have two blocks in our technique. The first one is in charge of detecting the system calls. We are using the Spark V8 architecture for our experiments, and in this architecture, system calls are initiated using trap8 instruction. So the contents of the instruction register is compared with the machine code corresponding to instruction TA8, and if they are equal, we know that the system call has been executed. The system call number is specified by the contents of the global register G1, which is a part of a Spark V8 register file. We modified the Lion 3 VHDL code and extracted this information and passed it to our FSM model. The second block in our technique is system call sequence recognizer, which is in charge of tracking the sequence of system calls, and it will signal when the sequence does not match a legal sequence. This is performed by implementing a finite state machine which accepts any legal sequence and enters an alarm state when an illegal sequence is detected. The state machine is generated by performing a static analysis of the source code of the correct program to generate a deterministic finite automaton that recognizes all the legal sequences. We run Snapgear Linux on the Lion processor. On the Linux terminal, we execute our correct code and inspect the signals inside the FPGA with chipscope. For demonstration purpose, our correct code only includes 3 write system calls, which is system call number 4. As you can see in the chipscope waveforms, we have a signal named code started, which shows the time our code is executing on the Linux OS. The attack output of our FSM is equal to 0 after the execution of the code, and this means no attack was performed over the running code. Now we run our wrong code, which is same as the correct code with an additional read system call, which is system call number 3. As soon as the code is executed, a red LED on the FPGA board is turned on, and this shows the execution of an unexpected system call. By observing the chip scale waveform, we can see that after executing the unexpected system call, the attack output is becoming equal to 1, and this output turns on the red LED.